Welcome back. Corollary. If A is an n by n matrix, then Ax equals 0 has a non-trivial solution if and only if determinant A is 0. Well, onward. Suppose determinant of A is 0. Then, what did we say from the previous theorem? A is singular. Determinant is 0 means A is singular. Okay, that is, its inverse does not exist. Therefore, if you do row operations on it until you hit row echelon form, you will see that A is row equivalent to a matrix B with a row of zeros. Further, AX is 0 and BX is 0 have the same set of solutions because all we have done is row operations. They maintain the same set of solutions. If B has a row of zeros, then Bx equals 0 has a non-trivial solution. You see, you have a row of zeros, which means 0 equals 0, left and right. That's a true statement. Your last variable can be any real number, and you can build back to the previous. So you have infinitely many solutions. If Bx equals 0 has infinitely many solutions, then A also has infinitely many solutions. That is, A has a non-trivial solution. There will be something which is non-zero. So that's one-way proof. Determinant A 0 implies you have a non-trivial solution. Mind you, this holds for an n by n matrix, okay, for a square matrix. In the reverse direction, assume Ax equals 0 has a non-trivial solution. Suppose determinant were non-zero. Determinant non-zero means A is non-singular. Non-singular means A inverse exists. Ax equals 0, A inverse exists. You can solve for x. Multiply both sides on the left by A inverse. A inverse times Ax equals A inverse times 0. A inverse and A give you identity. Identity times x is x. On the right hand side, A inverse times 0. Any matrix times 0 matrix is 0. That is, x has to be 0. In other words, x equals 0 is the only solution, which contradicts the assumption. Remember, our assumption is that there is some non-trivial solution. Non-trivial means something non-zero. We are saying x equals 0 is the only solution, which is contradiction. So, where did we go wrong? We said Ax equals 0 has a non-trivial solution and assume determinant non-zero. So, that's a contradiction. Therefore, determinant has to be 0. Okay, so this is an important result. As long as you are a square matrix, Ax equals 0 has a non-trivial solution if and only if determinant is 0. This is an important theorem. Notice you need to have square matrices. Well, we are not, we can't define determinants for non-square matrices. The reason I'm pointing it out is that if A and B were non-square, you can still get by multiplication a square matrix here. But here, to even calculate determinant, you need square matrices. So, start with the statement. If A and B are n by n matrices, then determinant of AB equals determinant A times determinant B. I repeat, determinant of A times B is determinant A times determinant B. Okay? If A is non-singular, that is, you see, A is non-singular means you know that it can be using row operations. Reduced row echelon form will be In. That is, A is row equivalent to identity matrix. That is, you take A, multiply, you see, to a bunch of elementary matrices, you should get identity. In other words, A itself is you see, multiplying by a bunch of elementary matrices, A itself is a product of elementary matrices. Okay. Determinant A. We know that for elementary matrices, determinant starts splitting off. Therefore, determinant A equals determinant EK minus 1 all the way until determinant E1. Now, B is some other square matrix, we don't know, A times B. A times B is A being product of elementary matrices times B. So, determinant of A times B is determinant of these guys. So, now here is the catch. Let me go back to a theorem we saw not long ago. Here. If you have a bunch of elementary matrices, multiply to any matrix. As long as they are elementary matrices, you can start splitting them off. Okay? That's what we are looking at. Okay? So here are all elementary matrices to multiply to any matrix. As long as these are elementary matrices, you can start splitting them off. Determinant EK, determinant blah, 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 until determinant B. But notice, these are exactly determinant A. The first collection put together is determinant A. Okay? So, determinant A times determinant B. So, determinant AB equals determinant A, determinant B. When did we prove this? When A is non-singular. Now, suppose A is singular. Well, we just saw in one of our previous results, if A is singular, then determinant has to be 0. Let's go back and remind ourselves. Not this one. There. A non-singular, if and only determinant non-zero. The consequence of it, A singular, if and only if determinant is 0. Okay, so that's what we are using here. If A is singular, then determinant A is 0. Moreover, A is row equivalent to a matrix C with row of zeros. So, row echelon form of A ends up with a row of zeros. That is, row operations on A will give you a matrix C with a row of zeros. Okay. So, C is obtained from A by a sequence of row operations. On the other hand, C times B, I'll take all of this times B. Notice the A. That's all of this to A. Now, CB is row equivalent to AB. Okay. Now, C has a row of zeros. So, C times B also has a row of zeros. Think about it. If you have a row of zeros in the left matrix, then multiplying that, so a matrix on the left has a row of 0. Then when you multiply, think about it, write down an example. The product matrix will also have a row of 0. If you have a row of 0, determinant has to be 0. Okay? Determinant is 0. What does that mean? Determinant of AB also has to be 0 because these are all elementary matrices. Alright, these are all elementary matrices. So determinant of this is non-zero, 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 non-zero until here. Determinant here is 0. All of these give you non-zero determinant. So this has to give you 0 determinant. So determinant of AB is 0. Well, which is same as determinant A, determinant B. It doesn't matter what the determinant of B is. Okay? Determinant AB is 0. We know determinant of A is 0, you see. So determinant of AB equals determinant of A times determinant of B. Corollary. If A is non-singular, then determinant of A inverse is 1 over determinant. This is an important result. Suppose A is non-singular, then what do you know? Determinant A times determinant A inverse is identity. Well, what did we just say? Determinant of a product splits. Determinant of A times A inverse is determinant A times determinant A inverse. On the other hand, A inverse is I, determinant of I is 1. So what is determinant of A inverse? I want to solve for this. Divide both sides by determinant A. Determinant of A inverse is 1 over determinant A. Definition. Two n by n matrices A and B are similar if there exists an invertible matrix C such that A equals C, B, C inverse. This is a very, it may not seem important to you now, but this is a very, very, very important definition. Two n by n matrices A and B are called similar if there exists an invertible matrix C such that A is obtained from B by C, B, C inverse. Okay? Corollary. If A and B are similar, then determinant of A has to be equal to determinant B. Suppose A and B are similar. Then by definition, there is an invertible matrix C such that A equals C, B, C inverse. Determinant of A is determinant of C, B, C inverse. We know that determinant splits multiplication. So determinant C times determinant B times determinant C inverse. On the other hand, determinant of C inverse is 1 over determinant C. So determinant C, determinant B over determinant C. They cancel, you get determinant B. That is determinant A equals determinant B, which is what you wanted to prove. Caution. Determinant of A plus B need not be equal to determinant A plus determinant B. This is a very important caution. Determinant splits multiplication. Determinant does not split addition or subtraction. So here are homework problems from the textbook for this particular section. Okay, have a look at these, try all before we meet in class. Okay then.